Hello everybody, this is our follow-up recording of the series of Dotty internals, or Dotty types. It will be presented by Martin Odersky.
Okay, hi. So let me just arrange my panes somehow. How do I click that away? Let's go to this one here.
Display for Andre.
Okay.
One last thing.
Okay, good. All right. Okay. Just have to be careful not to step on the power cable again. Right. Okay. Good. So after having done trees and faces and periods with Dimitri 3 weeks ago, I thought I'd go right in the middle of it and start with types, which is of course one of the core construct, if not the core construct here. So I'll go mostly top to bottom and essentially explain things as they come along. You might wonder what this EQ type here is. So that's essentially our multiversal equality. With that definition, we have declared that we can compare types only to themselves and not to other things. So that's just essentially our internal scaffolding to reduce errors due to universal equality. Now, for the types, we have a helpful doc comment here, which essentially gives you a diagram of all the types there are, or at least the ones which are essentially common to everything in Scala. So what you see here is essentially a first distinction between proxy type and ground type. So a type can be a proxy or a ground type. And if it's a proxy, then essentially there is another type that it stands for. So typically that's the supertype of something. We'll see how other types can be proxies. Ground types essentially don't have any type that is in a sense more general than they are. Let's maybe start with the proxy types. So the most important of the proxy types are name types. So a name type is just essentially a type name, such as int or string, or possibly with a prefix. And such a name type can be, the int or string or these things, they are one specific kind of name types called type refs. So it's a reference to a type. And it's a proxy type because it's essentially it forwards to the thing the name stands for, which will be one of the other types. Okay. The other very common type are the family of singleton types. So if you write, for instance, x dot type, so the path that just refers to the name x, that's a term ref. So the prefix would be that's essentially a term ref that tells you what the x is. Then let me just maybe write this. So that's something like x dot type in Scala. So this type is, as you can imagine, something like c dot this dot type. So it's not an identifier that you refer to, but the this of either your class or an enclosing class. Super type would be super dot type. So essentially one of your super types. A constant type is something like 3. So the literal 3, it's a type. It's a singleton type that consists of the only the value 3. In Dotty, we can actually write this type 3. In Scala C, there's a zip around there where we're not quite sure yet. I think it will be 3, but maybe it will also be 3 dot type. But I mean, that's source syntax. Here in the compiler, we're concerned with semantics. So we don't care so much about that. Okay, the others are a little bit more esoteric. There's term param refs, rec this, and Scholen types. So maybe I get to them a little bit later because it's better if we also look at the binders of the types. So these are essentially references to bound types in some form. Okay, type param ref is the same thing. So then we have a refined type. So refined types are things like space class C, and then you have a type T equals S or something like that, or less than S, greater than S. or also you could also have refinements like Valix, some type U, right? So all these are called refinements. And then it's possible also that you can refer in a refined type to yourself, to some other members. So you could write something like, well, let me maybe just write it here. So instead of U, you could maybe write Valix this dot T, that's legal Scala. So that's essentially a recursive reference to the type itself. And in Dotty, we have a specific binder for that. That's a rec type. So essentially, the rec type introduces a name for the reference, for the recursive reference, and then this refers to this thing. So the this in a refined type, that would actually be a rec this. So this type to a recursive type that gets specified in the thing here. Okay, so that's the refined types. Then we have higher kind of type applications. So they are a bit more specific. So that's something like if C is a type variable, then let's say C of string or C of T, that would be a type application. And there's one important thing here, which is corresponds to some of my talks, that if you write something like list of string, let's say, then you could also think that would be a type application, like an apply here, but it isn't. It really gets referred, that one would get translated to a refined type, in fact, where essentially we have a mangled name for the element type. If the original name was T, this would be called list.t, and then because that's, well, if it's non-variant, then it would be something like that. So the normal applications, they're actually all translated into refinement types, but then we have the higher kind of applications where the prefix, we don't really know what that is. It could be a type variable or a type parameter. And for those, we have this HK apply, which does these things. Okay.
So, Martin, so the distinction is that if you know that list is a list, then you do it directly, and if you don't know,
so if the prefix,
which part is unknown to require the higher kinded apply?
Exactly. So if the prefix is a type ref, which is possibly an alias of a class, so it refers via aliases, either directly or via aliases to a class, then we use the second thing, the refinement type, because those classes, we would know that they have these member types. But as long as we don't know what the prefix is, so it could be a type variable, say, a type parameter, higher kind of type parameter, then we write HK apply. So in that case, the prefix is always a higher kind of type, and that's what essentially the name HK stands for here.
Okay, thank you.
Okay. Then we have, I get back to the things I skip at first things. We have annotated types, so T at annotation, so that would be an annotated type. We have type variables, so those are, you don't write them as a programmer, but they're used for type inference, so there's essentially placeholders for types that we need to infer. And finally, we have type lambdas, so higher kind of type lambdas. For these, we have syntax in Dotty, so that looks like something like, well, if you wanted to write these, so well, let me write something which is not as so let's say we want the type that takes a type parameter x and gives you a pair of x and x, then that would be the type here. So that's a type lambda, higher kind of type lambda. That's the source syntax, and the type constructor is this thing here. Okay, some of the types that we have are not strictly types that we write in source programs. So for the types that we've seen so far, we call them value types. So they're possible types of values. Higher kind of type lambda is not a value type, so that would be a higher kind of type. So that's the second category. And then there's some types that essentially are not so much types of expressions, but essentially types of types. But we mangled them all in the same hierarchy because it turned out to be more complicated to distinguish them than to put them all in there. So a type bounds is a thing that consists of a lower bound and an upper bound. So if I write two bounds as a programmer like this, then essentially those two bounds, let's say we have a variable x, type variable, then what the compiler would treat this as, and we would say, well, this is a symbol, and the symbol has a type, an info, and the type of this symbol, which is itself references a type, that is a type bounds. So it's a thing which consists of a lower bound and an upper bound. Let's call this u. Oops. No, sorry. Okay. The other type that also is strictly speaking not a type of values is an expression type. So that's something like arrow t. So for biname parameters, or if I have a parameterless def node, so def f equals something like that, then its type would also be an expression type. So that's essentially it's a thing that when evaluated gives you the type t. Okay, cool. So let's see in what order do we do that. Yeah, I can fill this in. I can fill this in here. Yeah. So we'll have a look at the detailed things later. But if you have a look at the higher kind of type lambda, maybe let me see. Let's do this. I just have to find. Yeah. Okay. If we look at the what a lambda type is, then actually we'll see there's a whole family of them, depending on whether the parameters are types or terms, so the term lambdas and type lambdas, and whether these things are higher kinded or first order kinds, so star kinds. So a normal type, a term lambda, that would be what we call a method type, the type of a method. A normal type, and as a type lambda, is the type of a polymorphic method, so that's called polytype. If the result of the function that gets returned is not a value but a type, then we are at the higher kind of types, and we have here higher kind of type lambdas and higher kind of term lambdas. That one is actually not yet populated, so that's some project that we might do in the future to actually look at term-dependent types, but we don't do that yet. But anyway, all these types, they share a thing that they say, well, we know what the parameter names are, so that's a thing here, and what the parameter infos are. So that's, in the case of a type lambda, it would be the bounds, and in the case of a term lambda, just the parameter types. And they have a result type. So that's essentially the three identifying pieces of a lambda type. So what you see in particular then is, so for instance, the type, what did we have before? The type X.
I wonder if they can hear us,
yeah.
For some reason. Andre, you say you can't hear us. Why? Can you hear us now? Okay. Rome decided to die here.
Okay.
Okay, cool. Okay.
We're going to start broadcasting the desktop again.
Which one?
Triple points. Show this one.
Okay. Okay. Good.
Okay, good. Yeah.
Okay, cool. So we were at the lambda type. So I had the lambda here before, so that this lambda here. So that would be, if we write it out, it would be a. Let me just. Oops. I don't know why this doesn't work, but anyway, it seems IntelliJ is very picky with comments. Okay. Okay, whatever. So that would be a, what would it be? A HK type lambda in this case, where the param names is essentially just the, well, they are names, not strings, but I write them as strings. So that's just the, oops, list of x. The param infos would be, what would that be? That would be a type bounds with the lower bound nothing and the upper bound any, right? And what would the result type be? That's interesting. Now the result type would be a, can somebody guess what the result type is? So the result type is, it's a pair. So this thing is, instead of a pair, let's write it out. So that would be tuple 2 XX. Is it tuple 2 currently, or is it hcons? Sorry?
It's not merged.
Sorry?
It's not merged.
It's not merged. So for the moment, it's tuple 2. So this is before h lists. Okay. So the result type would be tuple 2 XX. So what is that? So that is a refined type. What's the parent of the refined type? That's a reference to tuple 2, so that we would have type ref, and that would be, the prefix is some reference to Scala. We have a look what that is, but essentially the name is tuple 2. Okay. And then the refinement says we have essentially, we need to say what the name is, so that would be probably tuple 2 dollar, what was the first T1, I imagine, the first element type of the tuple 2. So so that refined, sorry, what's tuple
T1 and T2.
T1 and T2. So the T1 of the tuple 2 would be what? So it would be a type. There's actually a type alias. A type alias is actually a type bounds where both bounds are the same. And so it's the T1 is the same as the X. And that's now a type param ref of essentially this guy here. So it actually points to back to the lambda, and its type parameter is the first. So yeah, just have to do enough parents, close enough parents. Actually, we're still not done yet because, well, we actually have 2 here. So each refinement can only do a single one. So it's actually more complicated than that. So what we have is our two refinements. So a nested refined type. The parent is this thing here. The refinement, the first refinement is what we've seen so far. And the second refinement would be tuple $2 $T2, and that would be a type alias to the same thing here, type param ref. Oops, sorry, I'm having serious problems with okay. I'm having serious problems because the control and command key are switched on this computer because I'm now in Linux and I'm used to Mac. Okay, but that's essentially the basics here that you see. Okay, these types, they look really simple, but under the hood they're actually quite involved. So it's a HK type lambda. It has some parameter names. That's easy. Param infos is also easy. But then the result type is essentially a double refinement of a type ref that goes to tuple 2, and the two field types of tuple 2, tuple 2 $T1 and T2, they're both bound to type aliases, and the type alias essentially goes back to the type parameter of the lambda. So in a sense, this is De Bruijn numbering, right? So essentially we use a instead of introducing, let's say, symbols, we point to the types directly and use the number of the type parameter. So here we always use 0 because we only have a single one, but if there were several type parameters like x and y, then we would use type ref to the lambda of 0, 1, 2, and so on. Okay, so that was that. I think that gave you sort of a more in-depth thing. Now we have to grab the thing and go up again. Okay, so now we know what that is, what the type param ref is, and how we use it. To fill in the other places, well, you've seen we also have term lambdas like method types, and we have type-dependent parameters. So a type param ref does the same thing. So essentially, to refer to the type parameter of a term lambda, like a method type, we use a term param ref, and that also has this sort of De Bruijn numbering. It points back to the term param lambda and to the number, to the position of the parameter. Rec this, we have seen, is essentially the same thing. It points back to the record type, and in this case, we don't need a number because there's only a single this. And then finally, we have these Scholen types, and they are essentially produced in special circumstances when the typer just has to assume there's a name with there's a term, a singleton with a given type, and it will make one out.
Sorry, for the term parameter, it would be x.type, right?
Which one?
For the term param ref?
If we wrote that, our user-facing syntax for a parameter was x, then to represent the type, it would be x.type, exactly. Yeah. So basically exactly like a term ref, but term refs reference things that are essentially defined normally, and in the end they will have definitions and symbols and stuff like that. But we chose essentially to use for all type binders, we chose not to use symbols. So Scala C used symbols, but in retrospect that was a problematic idea because the problem is that you always tend to forget to substitute these symbols. So you have a tendency to have essentially to end up with unbound symbols in your types after some computations, and that of course is fatal. So by essentially using De Bruijn, or this essentially direct pointers to the types, we sort of enforce more discipline to deal with types, and that's less likely to happen by using this kind of data structure for it. Okay, let's look at the bottom half here. That's the ground types. So some of these are pretty simple. So an AND type is an intersection, P and U. An OR type is a union, surprise. A method or poly, so that will be a polytype, polymorphic method or method type. With the method types, we have two further subtypes of method types. That's an implicit method type. So a normal method type, you know what that is. An implicit method type would be something like implicit PU, right? So parameter is implicit. And a Java method type would be essentially the same as a method type, but we record the fact that this thing came from a thing that was loaded from a Java class file. That's important because some of the more subtle rules, how we deal with method types, how we compare them, have special exceptions for method types coming from Java. Okay, then we have a class info. So class info is basically everything in a class. So if you write essentially class C and then extends parents, yes, and then we have a self type, and then we have some definitions. Then the last part, so the parents, the self type, and the definitions, they would all be part of the class info type. So essentially, we record what's in the class. And then we have sort of the odd types out. So there's a type no type for when there's no type exists. There's different from no type. There's a thing called no prefix. So that's so no type basically means you shouldn't even ask the question what this type is. Whereas no prefix is, for instance, if we have x.type where x is a local variable, so it's not a member of anything, then that would be translated to a term ref, like You see that up here, so that's what a term ref is. And we would give you a no prefix here to say, well, it doesn't really have a prefix type. Prefix is local, and the name is X. Okay, so that's what that is used for. Then we have error types. So that's essentially if the compiler detected errors, then it produces error types, and it generally has the strategy that if some of the constituents of a comparison or something like that are error types, then it will suppress further error messages. So it will essentially just let it go, let it go. And there are wildcard types, which you see sometimes in error messages as a question mark. So wildcard types is basically, it's only used for types that sort of the compiler uses as expected types or something. So if it looks into something and says, well, I expect this, then if some of the things are arbitrary, undefined, then it uses this wildcard types for that. Okay, cool. Right, we can maybe, since we distinguish between proxy and ground, we can maybe have a quick look at what is sort of the underlying type of a proxy type. So for a type ref, what's the underlying type? So we have a reference to a type. So the underlying type is then always either a class info. So if the reference points to a class, then the underlying type would be the info of that class. Or if it's a abstract type or alias type, it would be a type bounds. And actually, that's probably something I should just add into this thing, because there's a subtype here that which we haven't seen, and that's type alias. So type alias is a specific subtype of a type bounds. So a type ref then points to its underlying type is either a type bounds or a type alias. Okay. A singleton type, so x.type, the underlying type is basically the type of x, as you can imagine. So it's just the Wyden type. Same thing for this type. The underlying type would be actually the underlying type would be a reference to the class C. A constant type, again, the underlying type is the underlying type is the type of the constant, int or a float or Boolean or whatever. A term param ref, so that would be again what is essentially given as the bounds, as the type of the term parameter. For a rec it's the record type itself. For a scoring type, it's also its given type. For type param refs, it's the bounds of the parameter. For these things, it's the parent. So if it's a refined type, then it's just the C thing. If it's a rec type, then it's what's in the record, in the recursive thing. For an HK apply, it's the prefix here. So essentially drop the parameters. For a type bounds, it's the upper bound, the H. For an expression type, it's the underlying type. For an annotated type, it's the underlying type. For a type var, that depends what's stored in the variable. If it's already instantiated, it's the instance type. Otherwise, the type parameter it stands for. And for a type lambda, it's a good question. What is it for a type? I think, yeah, it's the right-hand side. Yeah. Okay, so basically these things are used by some of the other things that essentially just go through underlying, because a lot of the convenience methods, they go through underlying type, and therefore sort of they do something interesting for all of these situations. So those were essentially, that's an overview over the
quick question about the underlying field. So I think, is it the case that if you want to operate on the underlying field, you sort of have to manually traverse the pointer, if you will?
Yeah.
Or do all of these classes, do they sort of automatically delegate different operations to the underlying?
Not automatically, but we can have a quick look at type proxy. So you see a type proxy. So that's what these types are all subtypes of. It has essentially a common underlying thing. And so there are other methods, which we're going to see in a second, that use the underlying. Well, maybe let's just look up one of these methods. Let me just look. Okay. or let's say type symbol. So that's a method that you probably will use quite a lot. That you say, well, what's the symbol that's associated with a type? So a symbol is essentially a thing that refers to a definition of some type. So that thing here would say, okay, so the type symbol of a type is, if it's a type ref, then we actually store it in this type ref. We'll get to name types in a second. If it's a class symbol, then there's a class field in the class info that essentially points us back to the class. If it's a singleton type, then that actually refers to a term, and we have chosen here to say, well, we won't actually follow that. That gives you no symbol. So that's not a type associated with a type symbol. But for all other type proxies, just go to the underlying. So for instance, now if you had a type like list of int, so you've seen that that will be essentially given, that will be represented as a refined type, and the underlying type of the refined type is the parent. So it will get you to the list thing, which is a type ref, and that's the symbol of that list thing will be the list definition symbol. So that's how you get there. And for the other underlying as well. So other underlying that we saw were things like annotated types, expression types. So essentially, if you have an annotation, it shouldn't matter. If you have a by name parameter, it shouldn't matter, and so on. If you have a higher kinded application, something like C of int, where C is a higher kinded type parameter, again, it goes to the essentially the function part, the type constructor part, the underlying, and eventually these things lead to the same thing. And there are quite a few methods that sort of behave like type symbols. So you could imagine, for instance, if you look for members of a type, so you have a thing of this type, and then you have a dot and a member, then that typically also goes to the underlying thing. So you look for the upper bound, or you look for the parent, and so on. And there are quite a few others. So that's why essentially these type proxies, they are pretty universal.
Okay,
Other
thank you.
question? Okay, maybe we go into some of the methods that we have on types. We could stay right here. Yeah, so we saw type symbol. There's another one called class symbol. So type symbol just gives you, as I said, essentially the next available symbol of the type, going up the type proxies. And class symbol is to essentially to look for a class that's associated with that type. And that has these things. Well, maybe actually that goes too much in detail. But you see the same thing for class info. We get the thing. Now for singleton types, we get no symbols. Yep. For type proxy, we get the underlying. And we have special treatments for and or types here, where we say, okay, if we have an and type, let's say, and both of them refer to classes, then we say, well, if actually, let's say we have a class, an and type like list and object, then it's reasonable to say the class associated with this type is list, right? So that's what this does, because it picks it takes the subtype. On the other hand, if you have a type like list and string, then there's no good answer, and it gives you no symbol. So that's what this thing here does. And for the or type, it would give you analogously the super type. So list or object would give you object as the class instead of list. Okay, and then there's another one which is slightly different. So that one now doesn't guess with super and subclasses. It can return you a list of all the class symbols that are found in the type. So that does something for and or type. It just collects the two. So the term symbol associated with the type, so there we say, well, it must be a term ref or a type proxy leading to a term ref. So if it's a term ref, you get its symbol, otherwise no symbol. Then you have the base classes associated with the type. So that's also interesting. That's essentially this concept of linearization, that you say, given a type, what is its class and all the superclasses in that type in linearization order. So that would again go with type proxies, it just would go step through the type proxy. If it's a class info, then we actually store the base classes of a class in the class itself. So there's a method that gives you back that. But it could also be an AND type and OR type. So if it's A and B, what are the base classes of A and B? So these are the common parent classes of both A and B. No, sorry, that's for the AND. These are the base classes of A plus the A classes of B, right? Because we have a type that essentially is both an A and a B. So it's a subtype of all the superclasses of A and all the superclasses of B at the same time. So we get a union here. And for an OR type, it's the opposite. So if it's A or B, then we get the intersection of base classes of either A or B. Okay, next one would be decals. So that's declarations that are associated with a type. So declarations are in a thing called scope, and should we jump to that? And a scope is essentially something that contains a set of symbols, and that the symbols we can either step through them with iterator or for each or filter, or we have things like lookup, which essentially given a name gives you the symbol that's associated with that name in the scope. Or sometimes, if you expect there are several, you can also do lookup all. That will give you all symbols associated with a given name.
So where do scopes live? Are they in the context or in the symbol?
Scopes?
Yeah, like who contains scope?
So what contains scope? It depends. So classes contain their scope, the scope of their members. So class symbols or class denotations of symbols, they contain a scope, and that's essentially the symbols that are defined in the class. But local scopes, so if you go through, let's say, a block and you define symbols there, they are part of the context. But essentially, class scopes are also part of the context, because the context tells you that essentially I'm in a class through a thing called the owner field, and the class then tells you what its scope is. So in a sense, the context gives you all the scopes that are currently visible, and some of those scopes, they are maintained in classes because we need them later when we essentially select members of those classes.
And a minor note, after typer, context does not maintain the scopes.
That's right, yeah, that's only during typer, yeah. Okay, good. So that's so the declarations then are to say, well, if it's a class, then just look in the class. If it's a type proxy, then go to the underlying, and otherwise it's the empty scope. A declaration says essentially it's like decals, but it looks for the symbol corresponding to a given name, and that forwards to find decal, and find decal has a similar structure to decals. So it will, if it's a class info, it will go through the class to the class scope, and yeah. So that's I probably have to go to the exact things later. There's the other thing. So we had decal. So that's essentially the thing defined in something. And there is member, which is more commonly used. Sometimes you need decal, but more often you need member. So member is the things defined or inherited in something. So essentially what Java and Scala calls members are things that you also can inherit from superclasses and super traits. To find a member with a given name, what you do is so we're always in types. So you take a type, and you take a name, and you say, well, type.member name, so that gives you a denotation. So we'll have to get to denotations later, but for now, a denotation, so there was a problem in, a pitfall in Scala C, and that is, so if you have, let's say I have list again, and I have XS, and that's of type list of int. So then the question is, I do XS.head. What is that? And in Scala, the answer was if I do the find member or the analog of find member, that was a symbol. So that would give me back a symbol. And then I would ask, what is the type of that symbol? So that's a symbol. And if we do essentially take the type of the symbol, what would that be? Well, in Scala, it would have told me T, where T is the type of the list, because, well, I look up head and it has type T. And that's what was a very, very common mistake. The bad thing is things seem to work really, really good as long as all your tests are simple. And once you start to get into parameterized things and so it makes sense. It makes no sense whatsoever. So it was an extremely popular newbie mistake to just do that. So in Dotty, you can't do that anymore because what you get back from member is not a symbol like what we got back from Scala C, but a denotation. And a denotation is essentially a thing what a type or a reference means, and that is typically what it means depends on the context. So that's also why you have here a context parameter. But what the denotation typically would tell you here is probably the head symbol, so the symbol head. How do I do this? Symbol head, something like that, just to take some liberties how I express these things. And it would tell you at the same time it would have an, so it's a denotation. And in that denotation, we know that it has a symbol field, and that is head, and it has an info field. And the info in that case would be essentially type ref, Scala package reference, int. Right? So that's how it would look like, that denotation.
And can I ask, so, and without, if we don't go through the notation, if I were to get just the type of xs.head, would that be a term?
That would be the type of xs.head would be would be int in that case, no? Yeah. It would be, well, if you look at it in a debugger, then I believe what it would be is xs.list $t. It's the list $t member of the XS, right? So because XS is of type list, and then if you take a member, then that was the head thing was list $t.
Okay. And what's the representation of that? It's a term ref, type ref.
That's a term ref. Sorry, that's a type ref. So the name is list $t, and the prefix is the reference to this XS. So let's write it out. So that would be type ref, term ref, XS. Let's assume it's local, so no prefix XS as a name. And the name here would be list $t, or whatever the name of list is, the mangled name. I'm cheating a little bit because normally the mangled name is the fully qualified name of list, so it would probably read scala.collection.immutable.list. No, Scala$collection $immutable$list $t. That's what it would do. $t, I think. Yeah. Anyway, they are these manglings, and they don't really. They could be anything. It's just a way to reference to these things. Okay. So, but the point is, what this thing is then, if you look at its type, its info. So this thing is what? It's a type alias, which says, well, that's a type alias to type ref Scala int, right? So if you de-alias, then that's what you get. You get the int type. But if you take the type directly here, then that would be sort of the unalias type would be just that, what the type, what the thing gives you back. Maybe have a look at de-alias because, okay. So that's another method that is very commonly used. So de-alias is essentially, it takes.
If you go through member, the notation, that already de-aliases it for you?
I didn't catch the first half of your phrase. What already the aliases is or not?
So if you go through member and you get this denotation,
Yeah.
it will that de-alias it for you?
No, I don't think it would. No, no. Typically, we never de-alias because in this case here, if it's mangled names, then yeah, probably it doesn't matter. But for user-defined names, we want to keep the aliases because otherwise the users
Okay.
might be surprised to see a type that they haven't written.
Okay, but so you mentioned this bug that people often had in Scala C that they don't have anymore. So what's the bug and what's the fix?
Ah, okay. So let's. So in Scala C, the bug was that essentially here, when we write that the type of this thing is typeref XS list $T.
Yeah.
Then that type is the same thing as int. It's just an alias of int. So we get the precise type. What Scala C did was, if we take the head, then we got a symbol, and a symbol is something that's defined in class list. So we forgot that the prefix was XS, right?
Okay.
It's the head symbol, and then if we follow its type, then we just get the T, the list,
Okay.
essentially the local thing in list, which of course is not even bound at the point where we do the member. So essentially we get just an unbound type symbol, which is
okay. Right. Okay.
Okay.
Thanks.
Okay, so that is member, and so essentially what we have here is we have both member and non-private member. So sometimes we want to exclude the private members because, for instance, we come from outside the class, and then when we the member excluding, which is the thing that's called by both of them, that in turn calls find member. And find member is sort of the core of sort of member lookup as far as types go. So essentially they have, now we have 3 parameters. There's a name that we look for. There's the prefix type, so that was essentially the prefix where we started with. That would have been the XS, for instance, here, where we say, well, that was the thing on which we did the dot. And then there's also a flag set, which is excluded, where we can exclude some of them. So private, for instance, is a flag. So if we want to exclude privates, then you see here the flags.private. We put it in a flag set and said, those are things to be ignored. And then we have a long thing, which is a tail recursive go method, which essentially does something hopefully intelligent for each type. So for instance, here, the first one say, well, if you have a refined type, so that was, remember, C, and for instance, type T could be equal some S or bounds S. And if what we are looking for, so that's the underlying type, and we were looking for a .t, then, well, yes, we found something here. So we said, okay, we found a refinement with this thing, so we go to essentially the refined type, and that refined type, that's this one here, which is actually pretty subtle, so maybe I skip it because I think initially it's important to just know how to use things. So that was the refined type. This type, type ref, so most of them actually go to other things. Type ref goes to the denotation and does a find member there, so that sort of takes us out of types and into denotations. So the go things, maybe we shouldn't go because that's all internal what we do here.
Or maybe we should show the connection between types and trees through type assigner.
Yeah, we could. Should we do that? Maybe I want to just go quickly through the. Let's see, how much more of types do we want to see? I think there are a couple of concepts that we should have a look at. So, but I'm concentrate more on the API and not so much on how things are implemented. So we have seen we can look up a member. The other thing we can do, which is less efficient but sometimes needed, is we can essentially look at all names of members that satisfy a certain predicate. And so, for instance, here are sort of concrete instantiations. So we can say, well, give me all abstract term members. So that's all defs or vowels that are abstract. And that one would be all abstract types in this class. All type members that are not inner classes, all type members whatsoever, all implicit definitions, all member classes, so that's the classes that are members, all fields, and we can have a general thing with members based on flags where we set all members that have these flag sets set and these flags unset. So these all go through this member denotes thing, which is sort of the local implementation. And that goes through member names, which essentially sets up a name filter, which essentially uses all these, reflects all the conditions that you see here and produces the names. It's done this somewhat convoluted with the name filters because for efficiency, we definitely don't want to compute these each time you ask. So there's actually a heavy caching going on in the classes, which say for a given name filter, if you ask that question before, then we will give you the same set of types without recomputing them, because otherwise it would be way too inefficient. So that's why it's done with these name filters. Okay. Yeah, and then we have another one which is core, but often already rolled in the denotations. That's this as seen from thing. So again, if we have this previous thing that we say xs dot head, what's its type? So that would be essentially a thing that we say, well, we have the type list $t or something like that, the term ref, and we make this an as seen from. Well, let me just write this. Yeah. So that's the term ref that we have here. That's what we found in the head. And then we produce an operation as seen from, and the prefix type was xs.type, so that's our prefix, and the class is essentially the class containing this definition, so that would be list. So as seen from is one of the, I would say, 2 or 3 core methods in Scala that essentially determines how a type that we see in some base class gets transformed when we have a complete prefix. So with all this would essentially give you, instead of list $t, it would say, well, that's not the, yeah, so that would give you the thing that we've seen before, that it's the XS, the term ref XS, and then it's $t in here. So that's the thing that massages the types. Often, as seen from, is essentially already rolled in when we take denotations. So essentially, we always do that. So it's not very common that we have to do it by hand, but sometimes we have to, and that's why it's still here.
I have a question.
Yes.
So why it takes a parameter class symbol instead of just using the owner of the type parameter?
Because it's a type. Types don't have owners. Sorry, this current type here doesn't have to be an owner. So here we are lucky. Because we have something that's defined in the type, but it could be other things as well. It could be, let's say, a function from T to T, a method type from T to T. So we don't go in the type to find out what the owner is. So here we require that it's given explicitly. And sometimes the type doesn't even have an owner. So let's say, well, if the type already was list, like Scala.list, then as seen from would be invariant. It would still be Scala.list. Mm-hmm. So what we really need is the owner from the symbol that carries its type. That's what this class is, right? Yeah. So it's the type seen as if it were the type of a member of prefix type pre declared in class CLS. So if it's a thing of a definition declared in the class, it tells you how it's transformed by taking the prefix. Okay, so this was both basically the hardest part.
Similar question. So in this example, can you get the class from the type of the prefix?
No, you can't. The type of the prefix could be a subtype. So for
sorry. Okay, yeah, no, I see it now. Okay.
Type of the prefix. I mean, we had here XS was type list of int, and it was the same. But for instance, XS could be int list, where int list is a subclass of list that extends list of int. So you have to deal with these situations as well.
Okay.
Also, this method is used during the subtyping check when you assume that there are subtypes before you check that there are subtypes. So in practice, a CLS and the type may be even unrelated entirely.
Yeah.
Okay.
Okay. So the next bunch of methods has to do with subtyping. So there's less than colon less than, which says this type is a subtype of that type. And essentially that goes into, because subtyping is very involved, that goes into another class called a type comparer. There's a thing called top level subtype. There are many recursive invocations of this subtype thing, but that's how it's implemented here. So subtyping, yeah, I think that's also important because it happened. Maybe it's a little bit. Let's see. How do we? No, maybe we. Okay, I skip over that right now. It's difficult to keep a straight line with focus. So in principle, taking a subtype can affect your constraint. So for instance, if you have a type variable x, and you ask whether x is a subtype of whatever object, then the subtype check will say true, but it will essentially record the fact that you have constraint x to be a subtype of object in your constraint. So essentially it will just, as long as the constraint is satisfiable, it will give you back true and add stuff to the constraint. Sometimes you don't want to do that. So you want to say, well, don't add to the constraint. I want to find out whether things are a subtype without adding stuff to the constraint, and that's then called frozen, because there's a notion of constraints in the type comparer that the constraint can be frozen, which means I can't add to it, and that under that mode, essentially we have this frozen subtype, which is subtype and frozen, which compares them. Then we have same type. So is that the same type as that other type? So that means mutual subtype. So equals colon equals is just this is a subtype of that, and that is a subtype of this. It's again a big clarification with respect to Scala 2, because Scala 2 had essentially a notion which was not exactly the same as mutual subtype, but in Dotty, type equality is really mutual subtyping. You might ask, what happens if I ask t equals u for type t and u? What do you think you would get? That's just essentially you will see types at case classes, so that's essentially just the structural equality of the. Sorry, it's even. Yeah, it's basically whatever types declare, but it's mostly structural equality, or some types say it's reference equality. So equals is used for comparing types as a data structure internally. For instance, have I already computed this exact type before, and can I use some info about this type for caching or something like that? Whereas that is essentially user level equality. So if the type rule specifies that two types should be the same, then it's an equal colon equal. Okay. What do we have here? Oh yeah, that's used in some situations where we say we also allow you to essentially have comparisons like int is a subtype of long or things like that, which in the answer is yeah, not really. I mean, int and long are unrelated types. There's an implicit conversion from int to long, but in some situations we want to sort of count these things as subtypes. So that's the is-value subtype methods that we have here. Okay, so yeah, there's some notions here, overrides, which is sort of like subtyping, but for the override, for the purpose of overriding, we say parameterless methods and methods with empty parameters. So parents T, error T, and T, they are seen as overriding each other. So there we typically say that a vowel T, so that would have the type T, can override a def T, which would have this type. And because in Java, some of the types, like toString is actually a method, so it has a type like this, we throw that in as well. So we say a val toString and a def toString and a def toString with open parents, closed parents, they're all considered to override each other. Okay, right, and matches is essentially that essentially means for the whole type that the type is considered to be a legal type for an override of something that has that type. So, okay. Okay. Let's see, what do we have then? Yeah, base type ref is also important. So let's see. So we know already the types. So let's say we have class C extends some prefix D. So then if we ask, well, what's the base type of, or parent type, or transitive direct or indirect parent type of class C, then we might be tempted to say it's D, but that's not actually true. It's pre.D. We need to keep the prefix, and that's basically what base type ref does. So if you give it the symbol D, and it will infer the correct prefix for the type as a base type. And finally, we have subtype related and or. So that's essentially the greatest lower bound and least upper bound of two types. And there's a tricky one called safe and. So generally, one large cause of complications in particular typer and related things is that you might get cyclic references on evaluation. So if you ask too many questions, you go too deep, then you might essentially go back to a type that you're currently computing for a symbol, and that manifests itself in a cyclic reference error for the user. So users don't like that, of course. So that's why the all type algorithms have to be extremely careful, essentially where they look, because you might be about to evaluate something, and by looking at this very thing, you might cause this cyclic reference exception. So that's why some of the things are sort of either have variants or special precautions to do this here. So for instance, here we say, okay, we want to make an AND bit, but an AND is actually quite inquisitive. So if we look at the implementation of GLB, it would do all sorts of things. It would try to simplify the AND. It would say, well, is one a subtype of the other, in which case I only need essentially the lower one, and so on. So essentially that one really looks at all the parts of types, and sometimes you're not allowed to do that. So there's safe AND, which just says for the upper bound, just form an AND type. Don't ask questions. Just form the AND type, which corresponds to the AND. Don't try to simplify. For the lower bound, we can't really have these cycles there, because the cycles typically come from F bounds. Like if you have a type parameter X less super type C of X, so that's sort of that's sort of the situations where we can have these cycles. For lower bounds, we can't do that. So there we can actually be more conservative, more aggressive, and just form the union of the two. Okay, so that was subtype related. Let's see how much more do we want to do here. I guess that's also, yeah, there's a lot of things are important, so let me just go through the next part as well. So that's unwrapping types. So we've seen in Dotty what the compiler infers. For instance, it has a variable x, and you ask the compiler what to infer of it, what type to infer, then it will essentially do something very concrete. It will say, well, the type is x dot type. It's a more specific type I can find for it. And that's typically not what you want, because you say, well, yeah, sure, the type of x is x dot type, but I want to know, is it an int or a string or what? So that's done essentially with these unwrapping types, typically widen things. And there are a number of things that all essentially go through to some of the underlying types of things you have. So the most basic one is to say, well, if it's a type variable, then we want to essentially go through to the type that the type variable references. And so let me just, that's actually overloaded strip type. Right, so here, essentially this strip type var, it's overridden in type var. It's a type var class that you see here. Where it says, well, it's essentially, if I'm already instantiated, it's the instance, and if I'm not instantiated, then type variables correspond to essentially one of these type param ref parameters. So they correspond to a parameter, and then they say, well, if the type variable is not yet instantiated, then it gives me the parameter instead. But in both cases, the type var is essentially out of the picture. Okay. Related also, something that doesn't do much, strip annotates, as you would guess, if it's an annotated type, the annotation gets stripped and you get the underlying type, otherwise nothing else. Strip poly, so if it's a polymorphic method type, you go to the result type. And now we come to the more common ones. So the most common one is probably widen. So widen says if it's a singleton type, so you remember what singleton types were. So generally, a lot of the terminology really refers to this thing up here. So it's good to sort of have that always under your eye if you work with types, to say, okay, what's a singleton type? Well, here you see those things are singleton types, and that gives you a quick look. So all these singleton types, they refer to essentially something which is populated with a single value, and we want the underlying type. So that's this thing here. So more precisely, it's widen singleton. So that says, well, strip type. So we always strip type vars because it says type vars. They should never block what we look into. If it's a singleton type, then take the underlying type, and that actually the underlying type could be another singleton type. So we have to be careful, because there are things like where we can write while x y.type, right? So that's perfectly good. So in that case, the underlying type of x.type would be whatever x is declared with, so it would be y.type. So we get another singleton type. Okay, so we have to do it recursively. If it's overloaded, then there's nothing we can do because we don't know what it refers to. So that's a special case in quite a bit of the compiler. Overloading makes things quite a lot more complicated, because essentially it means that some of your basic assumptions don't hold anymore. Okay, and otherwise it's this. And what widen also does is, if it's an expression type, so arrow t, it also goes to the underlying type. So that's typically what you want, that you want to get these things out of your way. Okay, the other ones are sort of more specific things, widen term ref expression. So that only they all do less than the general widen thing. Widen if unstable. So that means that that has to do with path dependent types. So if let's say x, you have x dot member t or something like that, but x is not really an immutable value. Let's say it's a variable, then this doesn't really make sense. So you can't take a part of a variable. So essentially it would get widened to the underlying type of x dot t and then the hash t. So that's what these things here do. Oh, I should say another thing which I haven't mentioned, but I think it's important to understand is relationship between source and types. So if we write a type ref of a term ref of, let's say, x and t, so that if we decompile it, so a term ref of x is x dot type, and a type ref is really the prefix hash t. Right, so that's what it is. It's x dot type hash t. Of course, in Scala we have a shorthand for that. We just write x dot to, but the compiler always treats it like that. So essentially, a type ref corresponds to a hash. The prefix can be either a singleton type, but then it's specifically a singleton type, or it can be an arbitrary class type. Then in both cases, type ref is essentially treated as the internal representation of the hash. Okay, so widen if unstable does that, widens column. If it's a column type, widens. That one is, yeah, that one is more tricky.
So, Martin, just on that topic, is there some classification of which types are type and which types are term types?
Yeah.
And are there some types that could be both?
Yeah, that's right. So you see this here. We have types and term types. So if we look for them, let's see what are types. So class infos are types. We've seen them.
Right.
Type bounds are types. And that's it. So that's the only two types. And term types, there are more things, term types.
I mean, shouldn't a type ref be a type?
Let me just check. No, because, well, no, it's not. Because a type ref is a type of a term, right? So if I am XS is of type list, then list is the type ref. So that's the type of a term.
Okay.
If I wanted to say, but that's a good thing because it's also a common error. If you say type t equals u, so the question is, what type do I associate with the definition t, with the symbol t? And the answer is not u, because u is a term type, but type alias of u, so which is essentially a special subtype of type bound. So it's a type.
Okay.
Okay. Yeah, that was a good question. Okay. So there's another thing, since we are at widening operations, which is a more tricky one. So that is if we have a union type, an OR type, then there is a number of situations, mostly type inference, that says, well, I want to get away from that and really take the least common supertype of that. I want to eliminate the OR, and that's what this widen union does. So essentially, we take in general, it will be it will be sort of the intersection of all common superclass types of this thing here. That's what you will get. Okay, and then there's another thing, d-alias, which is essentially part of the widening operations, which we have seen already. Okay. And then there's one which is sort of widen everything. So it says, well, I want to widen and I want to de-alias at the same time and do that recursively until the thing I have is definitely no longer a singleton nor a type alias. So that's that thing. So if I want to get rid of everything, that's what I use. Okay, I think that's pretty... Okay, so narrow is the opposite of widen. Sometimes I need that because I need a path. even if I haven't got a path. So let's say I need to do something, and it's essentially my prefix is C, and I want to find out what's the type of some X in C, something like that. Then I can't really do that if it's not a path. So essentially, narrow gives me a term ref, and that's what these Scholem things are for. So Scholems are essentially made up identifiers that have the given underlying type this, and that I can use as a path. Okay, yep, and okay. And then there's a bunch of things where, we'll get to that later. Okay, I think let's see, then we have essentially access to parts, but I think I can skip over that because it's more important to know the types. Substitutions are important, so I can substitute in a type, and there's a number of substitution operations that I can use here. The most common one is this one here, so it gives me a bunch of symbols that I substitute, and for each symbol I have a type that I essentially, if I have a reference to that symbol, a term ref or a type ref, I replace the term ref or a type ref with the target type in the type. So that's the most common one. The others you have to read the document. Yeah, so here we can, let's maybe go on. Okay, and now we come to type categories. So we've seen proxy types and ground types. That was one distinction. And for efficiency, there's another distinction, and that's whether a type is cached or not. So essentially, all cache types are kept in a big hash table, which is called unique types. And when I form a new cache type, I look at first whether I have the same cache type already in my type table. So that way I can make comparisons much faster, and I don't essentially generate a lot of, I don't need a lot of memory, because a lot of the common types are actually get repeated all over. I mean, you can imagine how often I write list or int or something like that. So these are all cached, and therefore represented fairly efficiently. So then essentially what we have is four types really, four fundamental base types. The type can be cached or uncached, or ground or not ground. So here we have cached ground types, cached proxy types, uncached ground type, uncached proxy type. You might ask, well, why do I have 4 abstract classes and not 2 traits, which would compose nicely? And the answer is efficiency, because these things are, so types are, of course, the core of this thing. So the whole essentially most of the cycles are burnt in type computations, and these things, that's pretty important, let's say, quickly to be able to quickly hash a type, or to be able to quickly form the underlying type of another type. I don't want to have essentially a trait dispatch, because that's inherently slower. So that's why I have 4 classes for this.
What determines whether a type class is cacheable?
That's the type classes tell you that themselves. So
No, I understand I understand the inheritance part. I mean, so suppose I'm creating a new type in the compiler. You know, what criteria do I need to think about when I'm determining whether it's cacheable or not?
Okay, so basically by default, most types would be cacheable. There's some very short-lived types. Well, there's some types where it's basically impossible, because it would be graph isomorphism. So if you look at, well, we have to get to this, but types that are not cacheable are primarily things like type vars, because essentially a type var, the compiler creates a huge amount of type vars. Every time it's unsure about a type, it creates a new type var. So it makes no sense to cache those.
Okay.
And then essentially with the caching scheme is so that if a type contains a type var, then even though it's a cache type, it won't end up in the cache, because The type variable will tell essentially when you try to form the hash that the hash is essentially not existent, and so it won't try to cache these things. So there's essentially we do our own hashes, and these hashes, they have two special values: hash unknown, which is sort of so that's the signaling value to say I haven't computed this thing yet, so let's compute it here. And there's another special hash value which says not cached. So for a cache proxy type, for instance, you say, well, compute the hash that way. All the individual subtypes will have methods to compute their hash. And if the hash is not cached, then essentially just give me the identity hash code from for the object, and otherwise it's the hash here. And if the hash is not cached, then essentially the type will not be put in one of these hash tables.
And do I need, so in the subclass, if I extend the cache proxy type, I guess I do need to implement compute hash, right?
Yeah. We look at some subclasses basically right now.
Okay.
Okay. Yeah, I think that's fine. Good. So let's see. In what order shall we look at subclasses? So the first one that comes up is name types. That's by far the most complex. So maybe we'll reserve that for a little bit later, and we look at some of the simpler subclasses first. Let's see, what do we do? Yeah, that's a reasonable one. So let's look at and or types. They're nicely concrete, so we know what they are, right? So here we have and type. So an and type has two. So it's a case class. It has two component types, left and right. We know it's a ground type, and it's cached. And here we actually have some behavior that's common to and or types. So we form a separate trait and or type, which essentially it captures some of the common behavior. Okay. So what do they have? Well, they have the compute hash method. And that thing, they typically all forward to some of the do hash methods. So do hash, there's a thing called hashing, hashable. And here we have the do hash, so that's essentially the compute. I know how to compute hash codes, so that one you give it two element types, and it will produce the hash code from these types and the hash seed. And the hash seed is, where is the hash seed? Here. That's essentially the hash code of the class that you're forming. So essentially your hash code will be formed from the class and type and the two element types. So that's the hash you're getting. But I mean, all these are really internal, that you're only interested in the fact that there's somebody doing it for you. Okay. So one thing which is maybe a bit weird at first is a lot of these case classes are abstract. So what's the point of having an abstract case class? I think a lot of people, they fall off their chairs when I tell them that we use a lot of abstract case classes, because they could never imagine that you would need such a thing. There's actually a good use case, and that is that if the case class is abstract, we get to define our own apply method. If the case class is not abstract, then the apply method is generated for us. And here we have to call our own apply method because, well, what we want to do here first is we want to check that the and type is well formed. So that's just an internal check to essentially make sure we don't do stupid things in the compiler. So we say the two components of an and type must both be value types. You can't form an and type, let's say, of a type bounds or something like that. And then we go into unchecked, and there we say, okay, form now a new cached and type. So that's this guy here. That's just a normal class, final class that extends and class, and call this unique thing. So the unique thing, that's essentially this thing here that does this entering into the common hash table here, right? So it says, well, if the type is not cached, if its hash is not cached, then the type is fine, return it. And otherwise, monitored, that's just for statistics. So the important part is the last thing is that there's a thing called find entry or update in one of these unique hash tables, which essentially will give us the original type if it had already been computed once. Okay, so that's how you generate an AND type, and here there's some other sort of helper methods which are sort of more incidental. Right. And then what AND types have, that's also typical because most types have a thing like that, they have a derived method. So derived method says, well, given an AND type and two new element types, build an AND type from that. And the way it does it is, again, it wants to avoid computations. So it says, well, if actually the two element types are the same as I had before, then just return what I have directly, and otherwise go through the creation method and make this AND type. These derived methods, they are called in a lot of type transformations. So for instance, if I have a substitution method in a type, so it goes through all the types and some of the things it substitutes, then you would say the likelihood is very large that given any type that the substitution method didn't do anything. So it will come back with exactly the same element types. And since substitution calls derived AND types, so derived any type, all types have a derived method, essentially it means that the substitution will produce, if there's nothing to substitute, it will produce the type itself and not a copy of the type. So again, we save a lot of memory that way. Okay, so it was AND type. OR type is pretty much like AND type. Then we have, what other things should we do? Should we go through more types? Is that something that is useful? I guess it might be. Let's see. In what order?
How much time do you still have?
I don't know. I think I think we're guaranteed another half an hour, and then we might get kicked out, but we might.
Okay.
Okay.
Maybe I just do since we have the focus on the types, maybe keep it on the types and we do the other thing another time. I would think. Okay.
So in terms of other things, you wanted to look at denotations, or what else is there?
Yeah, denotations and contexts, I think that would be the next.
Okay. So you want to do that for a third talk?
We could do that, yeah.
We also have type assigner, type comparer.
Type assigner, type comparer, yeah, there's more. Let's see, but I think it's probably useful to give you a quick rundown to types, because types is sort of the biggest block. And
yeah, let's finish types and then schedule something else for other topics.
Let's do that. So, okay, so I'll keep name types for the end. So I do some of the others first. So this type that we've seen, that's essentially just the this of a class. So it's fairly simple. There's nothing much to see here. Super type, the same thing. Constant type are simple. They just take a constant. As always, essentially, it's always the abstract case class and the cache subclass and then the unique thing. For all of these cache types, it's the same thing. And essentially, all you need to do if you wanted to find your own is essentially come up with a hash for the type. So that's this in the framework. Lazy refs. Lazy refs we haven't seen yet. So that's again has to do with cycles or breaking cycles. So let's say we have in some parameter lists, let's say that things like that happen in the collection framework. So we have, let's say, might have a CC parameter, higher kinded, maybe something like that, and then an X parameter, which is a subtype of CC for CC X, right? Things like that. So it turns out that if you're not super careful, a lot of the operations that we've seen before, for instance, any type proxy thing would not terminate, because here it turns out, well, this goes to the upper bound. The upper bound is a type application that goes to this. No, that actually would. Oh, yeah. Things like that. So you can be amazingly creative with these upper bounds. So it turns out there are quite a few situations where if you form the types according to the recipes that we've done, then you get yourself into a cycle, and that cycle will give you a Stack Overflow. So there's a thing in the type checker that essentially is called check non-cyclic. And that thing will essentially, that's a very important operation because it will flag cycles which are illegal and essentially break cycles that are legal, and it breaks them with these lazy refs. So a lazy ref is essentially, it would probably have something like this, CC of lazy ref off, something like this. So that would be the internal thing for the X type here, where we say, okay, the X type here, it's a subtype of CC of X, but that's a cycle. So to break the cycle, we essentially put in a lazy ref here. So a lazy ref gets a function that, when called, produces the underlying type that the lazy ref stands for, and that type is cached in this computed thing here. So in the myref thing. So computed says whether we have already computed it. Good. So that was lazy ref. The next thing is refined and rec. So that's essentially refinement types, and refinement types with internal references to other types. So a refined type contains a parent type. So that's before the refinement, a name, a refined name, and a refined info. And the refinement can be of a term or a type. So if it's of a term, this thing is a term name. You know what that is from the trees. You know we have term names and type names. So if it's a term, this thing is a term name, and this thing is a term type. And if it's a type, this thing is a type name, and that thing is a type type. So, well, it's actually more specific. In a refinement, it's always a type bounds. It's a type bounds or type alias. One of the two. Okay. The underlying type is the parent. There's a debug hook, which is essentially called from the creation methods, which sometimes when we want to figure out why things go wrong, we populate this with assertions, but right now there's nothing in there. There's a derived method as usual, so it says, well, if it's if all the components are the same as before, return this, otherwise make a new one. And there's there's an equals method, yeah, for structured things we have to give you an equals method unless it's already given by the type class. Why is it not given by the type class here? Actually, this thing I think that thing looks superfluous, right? Yeah, I think we did something funky before. We certainly did, and now we have much simpler refined types than before, and so we don't need an equals anymore. So I think this thing can go. Let's just delete it. Well, we only need the hash thing. And some of these things also have two-string methods. That, again, is actually useless because that's precisely what we do otherwise for the two-string. Yeah, so I think that can go as well. Okay. There's all these things then, if they're cached, they have this apply method, which is essentially just does the uniqueness hashing, and that one here would check the instance type as well. And and there's an assertion here which says assert not ctx.erase types. So what does that do? So we haven't seen context yet, but one of the things in the compiler is that essentially things are very different before erasure and after erasure. Erasure is sort of in the middle of the transformations, and after erasure, essentially we only have JVM types. So we don't have Scala types anymore. We don't even have Java types. We have essentially Java 1.4 types or JVM types. So that means that after that, we definitely don't have any refined types anymore, because that's a Scala thing. That's not a JVM thing. So again, in internal consistency check, if somebody tries to create a refined type after erasure, we should blow up, and that's what this assertion here does. Okay, and that thing here, this make thing, is just another creator. So that can make a refined type with many refinements at the same time. So it has a bunch of names and a bunch of infos, and including an empty number of names. So if it's empty, it's just the parent, and otherwise we go recursively through the thing and essentially give you as many refinements as you need. Okay, a rec type. So that was essentially, it's just a hanger to essentially for expressing references to within a refined type. So there we say, okay, that thing now gets, to form it, it needs to get a function from rec type to type. Why a function? Well, because in the refinement of a record type, I want to refer back to the record type that I just created. That's what these rec_this things do. That's what these binders do, right? So I can't do that because I'm about to create the record type. So the best thing I can give to the record type, to the recursive type, is to say, well, you tell me what you are. So your own identity, that's this record type, and then I tell you what your contents are. So that's the idea here. And the knot is tied here when we said, well, when we create the record type, we have this here, and here we just pass it to parent X, and that's then our actual parent.
So how is this used in practice? Like, do you call this function a lot, or do you call it somewhere and cache the result, or what?
Well, whenever we build a record, so the typer, okay, let's have a look at, just to, okay, let's see how it's called. Wait, wait. I thought I would see. Okay, let's. Okay. Oh no, it goes to the typist sign. Yeah. Okay. So now I would have to give you. Okay.
Okay.
Right. So here we have it. Yeah. So. Okay. Maybe go back to rec type, and I'll get back to your question immediately afterwards. Okay.
Okay. Yeah. Sorry.
So we have this rec type. It has a derived type. Okay, so derived type already tells you something to say, okay, gives you a parent type. If the parent is the same as the current parent, then that's fine. We can give you the current rec type. Otherwise, we have a problem that essentially the new parent type it typically will refer to the recursive type again, but the references, or that's the convention, are still to the old recursive type. So we have to substitute it out. So here we say, okay, to form the new recursive type, we pass it a function which says, well, given the identity of the new type that's formed, take the parent and substitute out the recursive this and in this parent from, if it previously pointed to this type, then now it points, its type is a rec_this to the recursive type that we are about to create. Is that clear? So if previously we had a reference to the current rec type, now we get a reference to the newly formed rec type. That's what this function does. So the reason when I talked about De Bruyne and things like that, so the big advantage is, so these things are subtle, these essentially self-references and things like that. The big advantage of the current scheme is that if you don't do things right, it's most likely a type error. If you don't do things right in the previously, it worked out fine. In fact, it looked simpler than the right thing, and you just got unbound symbols in the end because you were missing a substitution. Yeah, but essentially, because it forces you to write a function from RT, you said, well, since I get an RT, what am I supposed to do with this? Right. So it's fairly close to your head that you're probably supposed to substitute something. Okay, yep. And there's something which is a sort of a utility thing, which is referred to by, okay, let me get back to that. So creation method of a recursive type, there's a normalization, and then there's a close over. So close over says we have an expression which is potentially recursive. So given a rect type, it's a type. What we do is we pass this expression to the apply method. So that's this guy here. So this and apply is the same here, of course, because this is rect type, but that's I could also write apply rec x, parent x. And then I say, okay, I might actually have overshot because maybe this thing is not recursive after all. So that's what this is referred to by essentially computes, says, well, go through the parent that now is a concrete type. And if it refers to the RT, then keep it. And otherwise say, well, we actually didn't need a recursive binder. Okay, so that was the close over thing. Now it can go back to the type assigner where it's used. So that sort of tells you what the thing does. So this thing here is if it computes the type of a refinement type. So you have a refinement type expression, which is a tree, and it says, well, what's the type that corresponds to this expression? The first thing what it says is, okay, we have the parent type. So that's a tree, but we can get its type by just .tpe on the tree. So that you remember from the trees. So, okay, so we have the parent type here, and then we have a bunch of refinements, and for each of them we add a refinement. So that's this method here. That would just compute the refinement with the parent it gets, the name of the symbol. So trees have symbols, so that's the name that we have see in the tree and the info of that symbol. Okay. And then finally we say, well, that actually might have recursive references. And the way it's done is basically when we form this refined type, we sort of make up a dummy class. So the this of the type starts as a this of this class here, this refined class thing. So we say, okay, to actually finish the refined type and handle the mutual references, make a rect type, close over. So that means, well, if it's not needed, don't drop the rec, but otherwise use it. And what we do here is to say, well, we have a substitution operation of this, where the from thing, we give the class of which the this we substitute, and the target type is rec this of RT. So that's how it's used, and that's most of the usages are like that. There are a couple others when we like unpickle things from class files, then again we have some representation, and in the end we have to build a recursive type for them. But if they specify that they are recursive. Okay, back to types.
And sir, just the rec this, is that somewhere here?
Yeah, let's have a look maybe at that next. Yeah, that's good to keep them in pairs. It's logically somewhere else, but we skip ahead. So we essentially what we did is we bundled up all the references to some binder types in their own section. So here you find the rec this.
Okay.
So its binder is a recursive type, and it is a bound type. So it's one of these things that essentially need a binder to make sense. It's also a singleton type, and that's just essentially the general thing that for a bound type it has a type field BT, which is the bound is the type that contains the binder. That's a rec type. The underlying type is the binder, and then we compute the hash and the equals, and we have a toString. So toString, that's just essentially that we see something, because for the rec this is a case. Okay, yeah, rec this is a case class. So here we have to be careful, because since it's recursive, if we did the normal case class equals, it wouldn't terminate, because it would go to the recursive type that contains the rec this. So the equals thing would never terminate. So what we do is we say two recursive references are equal only if they have the same binder, where this is an AQ reference equality. So that way we break the cycle. And the same thing is for the hash then that corresponds to the equals. So you see the hash is essentially a hash that's based on the identity hash on the binder. So we say just add something to it. We take the hash of the binder and but the identity hash. So don't try to look at the structure of this thing because it's recursive and make that the hash. And the toString finally, so that we see something when we debug, we give you the hash code of the binder, because otherwise it would just say rec this. Well, if we use the normal toString again, it wouldn't terminate because it's recursive. So instead of telling you what the binder is, which we can't because it's recursive, we tell you what at least the hash code is so that we can compare two rec this of different things. And it can actually happen that because these things sort of get computed, as you've seen, the parent gets computed. When we create a rec type, there's actually a window where the parent is not defined, so it's null. So we handle that. So if you get a null pointer exception, and we get a rec this, and it says under construction. So we say, well, we don't really know what the current binder is because we haven't computed its parent yet. The parent is not computed yet. Okay. So that's that. Let me go back to class rec type. That was that. Yeah, maybe again one thing here that maybe is useful to look at. It's a bit out of sync, but still. So there are two fundamental sort of heavy-duty machineries that we can do with types. One is called a type accumulator, and the other is a type map. So basically, these things are fold and map for types, but they are classes. So a type accumulator has an apply method, which essentially tells us what we have to do for each kind of type. So what this accumulator here would say is to say, well, it's a fold, so so it's a fold, and the result type is Boolean. So you get a Boolean coming in, and you get a type, and you say, well, what should I do? And here, essentially, what this thing has to do is it has to find whether the type contains a reference to the current recursive type. So if that's already true, then no need to look further, so we're good. If that's false, then we fall into the second branch of the OR, and there we say, okay, what type do we have? If it's a type ref, then it could be in the prefix, so we should look deeper. If it's a rec this, then we say the rec type, so the currently enclosing rec type, that's what this rec type this refers to, right? Should be the same as the binder of this TP. In this case, it's a reference to our currently enclosing rec type. If it's a lazy ref, then we say true, because we shouldn't at this point follow lazy refs. That would again explode on us. So because as you've seen, we do this in close over when we ask whether a type refers to something. So if it's a lazy ref, we assume the worst and say yes, it refers to it. And otherwise, we have this fold over, which is sort of the canned method in the type accumulator for all the other types. We could leave this out as well. I think this one is just left in here because it's faster that way. We don't, because fold over is a megamorphic dispatch, so it's a bit slower. So quite often you see situations where before we go into the general case, we pick sort of the most common case by far, which in this case is type ref, and treat it specially. Have a look at fold over. So that's the type accumulator. A type accumulator is then essentially a function that takes is essentially a class manifestation of the fold left signature. So it says, well, it takes a T, which is the accumulator, it takes a type and gives you back the T. Okay, and then its core is essentially this big thing, fold over, which does something for each kind of thing. Type ref, term ref, this for this types, and for all the others, basically it always goes into the type. So let's have a look at, for instance, rec type goes into the parent. Have a look at refined type. What's refined type? Didn't see. Oh, Oh, there's refined type, yeah. So it goes into the parent, it goes into the refined info, and essentially goes into all the types. So that's what the type accumulator does here. One added detail here is that as we go into types with folds or with maps, we keep track of the variants. You know that variants sort of their positions in types, they have variances and variance strips at a parameter position and so on. So as a convenience, we keep track of that in essentially a protected var called variance, which we can query in some of the maps, and some of the folds actually want to know what the variance is. So that's why you see that here. But most folds and most maps just ignore it. Okay, cool. Let me just. Yeah, so that was the refined types and rect types. Okay. And all we had. Okay, cool. Then the next big jump is let's see. Yeah, so extra types are again simple. I don't even think I need to talk about it anymore. So that's just the arrow type, right? So okay, they have a result type. They have an underlying, which is the result type. They have a derived expression type, and they have something called compute signature, to which I also have to get later. Okay, and then we have these lambda types, which is where we've been before. So that's essentially the other big parts of types that all are type binders of some form. And I've already said, well, they can be lambdas of term variables or type variables, term parameters or type parameters, and there can be star types or higher kind types, and currently we only have those three. So we have this one here, higher kind type lambda, method type, and polytype. Higher kind of term lambda is not defined, but the framework sort of allows for it already. Right, so that's the base class. Maybe it's better to actually look at some of the concrete subclasses. Let me go to the... Okay, so method type. That's the first one. So method type, so that's a type of a method, as the name implies. So what do I need to know for the type of the method? So it's a bit, there's a crucial distinction when I write the method as a tree, something like def f, and I might have a type parameter and x t, result type unit equals block, blah, 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 and then we have a reference to x and a reference to t. Okay, so when I write these things, then those things will end up as definitions in the tree. That will be a type def, that will be a val def, and definitions have symbols, and I see in the tree I can refer to these things under symbols. So this thing is a type symbol, and that thing is a term symbol. But that's the view inside the function. When I'm inside the function, I have symbols. When I'm outside the function, I don't see these symbols anymore. So because they are essentially hidden inside the function. And in particular, the type of the function doesn't refer to these symbols. That would be indeed, that would get us into trouble because it wouldn't deal correctly with recursive invocations of this function and so on. So what we have instead, and that's now here, the type view is the outside view, is essentially just a list of term names, which is the param names. In this case, that would be just the x here. And then it would have a list of param infos. So that's essentially the t here. But again, we have to be careful because it could be dependent. So if we could, for instance, write y, and that's an x dot some inner type that is defined in t, right? X dot u. So again, in order to do it correctly, that thing could give us a recursive reference, which is called a term param ref. So to form it correctly, we need a closure. We need to say, well, give me the method type that you're about to construct, and I can tell you what the types of the parameters are. And the same thing, of course, for the result type, because the result type might also be parameter dependent. Yeah, so that's another result type expression. And then it says, okay, so that's a star lambda, so that's a method, a polytype. It's a term lambda, so it's over term things, and that thing here, I'm not even sure what that is. What is that? Arrow. Oh, it has an arrow. It has an arrow thing. Yeah. Okay. I, okay. Good. All right. So. Then, as usual, when we have these recursive things, we have to form the actual types. We have to tie them up. So we essentially pass this to our expressions here, and that gives us then the parameter infos. So that's essentially the types of the parameters, the result type, and yeah, and that should be a type that exists. So what does exist mean? Exists just means it's not a no type. So no type is sort of this placeholder which says no, we don't use null for these things because we want objects and objects of the right type. We say no type, which says no, that's there's no type to here, and that in this case would indeed be an error. So there's an assertion. Okay, yeah, and then we. All right. So the next thing with these method types is. That's essentially the problematic the subject of overloading. So well, no, okay, so yeah, no, let me drop this for the moment. Yeah, so there's a way to compute the signature of a method type, which is essentially something like what you see in class files. So it's essentially a string or a name. Well, it's called a signature, so it's a thing that consists of names, and it tells you about essentially the erase type of this method, which you need to know when you have several overloaded variants. You need that to know that to identify one over the other. Okay, and then we have subclasses for, so that thing is again one of these abstract classes, class things here, so because they are all unique. So there's a cached one, which is used to actually form them, and they are further subclasses for Java methods and implicit methods. We've already seen that. And then there is a there are companion objects, method type, Java method type, and implicit method type, which essentially given parameter names, the infos and result types, build method types of the right type. And there's a lot of funkiness in there. Well, not funkiness exactly, but a lot of functionality in the that's essentially just the base type of a lot of different ways to create these things, these various kinds of lambda types. But in the actual objects, it's essentially very simple at the end. Okay, that was the method type. Polytype is very much like a method type. So polytype has the polymorphic method. So now the parameter name size is a list of type names. The param infos, it takes a polytype, and it now doesn't give you a list of types, but we know more. We know that the type name, the type parameters of a polytype, their types are all type bounds, so lower bound, upper bound, and the result type expression. And otherwise, it's basically the same as the other polytypes. Yeah.
So are all the parameter lists curried into multiple types that are nested within each other?
Sorry, are all there?
So if you have multiple parameter lists,
yeah.
do you get method types nested within each other, one for each parameter list?
Exactly, yeah. So the result type of the method, so the outer method type would contain a single parameter list, and its result type would again be a method type.
Okay, yeah. And then same with the polytype, right?
That's right, yeah. So there's a thing called final result type, which which goes through it, and it forgets all parameters. Strip polys forgets type parameters, and that so that gives you the eventual result type, which is not a method type anymore. So that's one section that we've skipped so far. So there's some things which really apply only to certain types that we have as convenient accessors here, like the parents of a class type. So essentially, what are the parent classes? The first parent class, so that's the superclass. The self type as it's written for a class. The infos of the parameters, so all parameter sections, and the names of all the parameters, only of the first section, and so on. So these things are sort of always, they look at the type where they make sense, and give you some default value where they don't make sense. So sometimes it's useful to use these things, but they are sort of not super important as things. Okay, maybe I propose to do as a last bit a thing we've left out, and that was type refs and term refs. So essentially name types, and they are also the most complex ones. Let's look at type refs first. Okay, so you could say, well, that's really simple. That's our class type ref. So yeah, it has a prefix, it has a name, but all the complexity is in its superclass, name type. So name types is a common superclass of type refs and term refs. And term refs are name types and singleton types, as our diagram that we looked at the start of this session implied. And type refs are just name types. So name types is where it's at. That's really the thing with it, and that's also sort of the door to denotations and the other things which you have to look at another session. So a name type, in principle, it's very simple, and that's sort of one of the big changes between Dotty and Scala C. In Scala C, a name type has much more to it. So what constitutes a name type is really just a prefix and a name, and well, if it's a type ref, the name is a type name, and if it's a term ref, it's a term name. And but then the thing is, of course, when you have something like, let's say, scala.list, prefix would be a term ref referring to the Scala package. List is the name. Then, of course, you want to say, well, what does it mean? What do I get from this type? What's associated with this type? And that is essentially, so what Scala C did is it would give essentially a symbol. So, and the symbol is essentially a definition. So with the symbol you got the rest of it. In Dotty, we don't do that. And the reason is that, actually there are several reasons. One is to say, well, there was this problem with symbols that we actually got the wrong type because the symbol didn't contain the knowledge about the prefix, so that was what we looked at before. That we say if the name type is, let's say, term ref of head, xs.head, then if you want to say, well, what's its underlying symbol? That was head. What's its type? Well, let's list $t, and that's not the type we want. We wanted ints, right? So that's the one reason why we don't want to have a symbol as fixed in the type. And the other reason has to do with essentially IDEs and incremental compilation. That what we foresee is that the compiler will essentially run in the background of an IDE and constantly recompile things. And that means that in different runs, the user might refer with the type to a symbol that the user is currently editing. So in the next run, the symbol is something else. And that means that the type that we have that refers to that symbol is still the same type, right? xs.head, term ref xs.head is always just the head in x. But the underlying definition might be something completely different because the user might have just edited what head is, for instance. Or we might read a different class file into a resident compiler, and now when we read it again, it's something. So that's why we said, well, that's actually, the symbol is strictly speaking not information that is inherent in the type. The symbol is information that is computed from the type. So that's important. So that's why we don't have a symbol as a val, but the symbol is computed. And so it's computed, let's have a look at, well, oops. more is good. But what is it computed from? So the core thing here is really that we say, well, the type, like I said, it contains more than a symbol. It contains a full denotation, which means it contains also the underlying type and things like that. And that denotation is computed here, and it's cached in a field called last denotation, which is strictly private to name type. So to make it efficient, so essentially every time you want to find out what's the symbol of this name type or what's its underlying type, it will have to say, okay, let's compute the denotation of this type. You need to give it a context, and the context will tell it, I'm in that phase and in that run. At this particular phase and run, what is your denotation? Potentially, of course, a fairly complex operation. So typically, compute the denotation, what do I have to do? If I have a member and a prefix, well, normally I have to take this find member, this big function that we've seen before, and essentially look up the member and the prefix each time I do that, which is a fairly heavy operation because I have to look in the prefix and I have to look at all the base classes, have to collect all the definitions, have to join all their types, and that will give me the type of it. So to make this half fast, we have to cache heavily, and that's basically done to here that we said, well, if you have already asked this question in the current period, current run, current phase, then we know what the answer was, and we give it to you directly under last denotation. Okay, so to find out what the denotation then is, we give it a context. And the context, like I said, contains the current period, current phase and run. And it says, well, if the checked period where I've checked it is the same as what the period is now, then return last denotation. Otherwise, do the next step and say, return the denotation at the period now. Okay, so that's the next thing, the period. At the period now, it says, well, actually what we have in these denotations is a valid for window. So some denotations we actually know they're valid for more than one phase because we know there's nothing that transforms the denotation. So the next thing is to say, well, if valid for contains now, then that's fine. Set check period to now and return D. So all this is done, as you can see, sort of for really, because this is probably by far the hottest spot of the whole compiler because you need denotations of types all the time. Basically, every single operation needs a denotation of a type directly or indirectly. So this is hit extremely often. So the way we do it, here I actually counted that the bytecode is under 35, so it will be inlined and things like that. So here's where we actually looked at the generated bytecode to be sure that there's nothing too inefficient going on. And that's also why they're sort of split. So here we say, well, most common thing is it's just the current period, and then we can inline it and return last denotation. The fallback is slightly more complex, so it probably won't be inlined unless it's extremely hot, and it says valid for contains now. So there we have a set comparison. A range comparison, not a set comparison. And if that's still not the case, then we have to do more, and that's compute denot. And compute denot is then more complicated, and for that to understand what it does, I'm probably skip all these things because these have to do a lot with denotation. So they sort of compute how denotations get transformed by phases and things like that. But the big fallback anyway is load denot. So that's sort of the catch-all, which we could do in most cases, but again, it's sort of, because it's the most inefficient thing, it's the most expensive thing, we do so only if we must. So load denot then essentially says take the denotation, this is as member of, which says, okay, form with the name a non-private member of the prefix. No, sorry, that's this one here. Prefix dot non-private member name. And if we allow private, it's prefix dot member dot name. So that's how we finally produce the denotation for this as member of. And then, for instance, symbol. So that's the final thing that's the thing we started with. We say, okay, if we have the check period equals now, then we can take the last symbol. so it's again cached. Otherwise, we take the denotation and look in the denotation for the symbol. So there's a special case here that in some cases, we'll have a quick look at the creation. I sort of have a seed symbol to start with. I don't have a denotation yet, but I have a symbol, so that sort of, it figures out that the last denotation is null, so nobody computed the denotation yet, but we have a non-null last symbol, and that is somebody actually gave me the symbol, and then I can return that directly. That's sort of a corner case to do that. Okay. Maybe one thing, because we've seen it, just to show you that, so that's the basic scheme of name types. Now, let's have a look at the corner cases, what we have. So one problem with name type is if we have, let's say we do XS, and this is it's a string, and we do XS dot substring. Okay? So there are actually a number of substring methods in strings, so there's not just one. So if you have a term ref whose prefix is a string, so a string value, and whose name is substring, we don't know which one it is. So we have to be we have to disambiguate that somehow, and that's done with so-called signatures. So there is a where is it? Right, so there's term ref, and then there's term ref with signature. So that's a subtype of term ref, and that gives you the prefix, a name, and then it has a signature that essentially tells you what the name is. And that has essentially the so that way you can figure that out. Let's see. What was? Oh yeah. So right. So what it does, it overrides this load denote, which just does the member. So if it's overloaded, then there's actually a special kind of denotation which says this denotation is overloaded. So it doesn't have a single symbol, it could be multiple. And in that case, it tells you what the possible alternatives are. So what are the symbols and what are their types? And an overloaded denotation has an overloaded signature. So that's just a special sentinel value. So we say, well, if the signature here, no, sorry, if the signature where we want this thing is overloaded signature, so we say, well, give me the overloaded denotation. And if not, then denotations have this add signature method, which says, well, give me a signature, and I give you sort of the sub-denotation that matches the signature. So one of my alternatives that matches the signature. And that one is you will get back. Okay. So that's the signature thing. So you see for term refs then have in general a signature method, which is essentially the signature of the denote. You might say, well, what if it's like yeah, oh no, we get the signature another time. And a term ref can tell you whether it's overloaded, and if it's overloaded, well, in general, it can give you what alternatives it consists from. If it's not overloaded, this will just return a singleton list with one alternative, otherwise several. And again, for efficiency, we can actually give you all alternatives with that match a certain predicate, because it turns out the list of alternatives is not stored as a list, it's stored in some other thing, so it has to reconstitute it as a list each time we ask, so it's more efficient to already give it a filter predicate to push that into the thing. Good. Yeah, there's one last thing with which I want to leave you just before you run away crying. And that's where was this thing? Right, select.
Can I have a question?
Yeah.
Question? Is there any chance the denotation to change within a phase?
Sorry?
Is the denotation, does the denotation change within a phase?
No, a denotation is an immutable thing.
Okay.
An immutable denotation is the meaning of something, and typically the thing will have different denotations in different phases. But a denotation is something immutable. A denotation typically consists of, if it's non-overloaded, of a symbol and a type. It says, well, it refers to this symbol and this type. Sometimes the symbol is missing. If there's no unique symbol it refers to, then it's just something with a type. Yeah.
I can think about denotations as the entire history. It may have a new value, but it will remember both the old and the new.
Okay, so there's one thing which is really tricky, and that is, let's do this way. We say class C val x, and then we also have a private shadowed, yeah. Let's see how we do this. Yeah. Class. Yeah. The extends C. Yeah.
So we're gonna get kicked out in about 5 minutes.
Okay. I'm basically yeah. Good. I'll act accordingly. So here's a problem. You could have a visible thing like now the question is what is d dot this dot x. What is that? So we said that a type refers to something, and what it refers to should not depend on where I use the type. So a type, a term ref, sort of it contains a binding, it contains a denotation, and that tells you what it is. But here we actually have a problem that we say if we do d dot this dot x, if we're inside class D, we will see this private val. If the type actually is maybe in a subclass of D where we can't see the val, we actually mean the val of C. And so that's a big problem. So that's what we have these. We do that in the names that we say we have this. Essentially, it's a shadowed name of X, which says, well, we're in class D, but we don't mean the private name X here, which we otherwise would mean. We mean the public name that's inherited, or that's an inherited class. So that's what these shadowed names things are. So if you see that, then keep in mind that that's what it is. We had that at the load dnot, right? Yeah. No. No, super load dnot. Yeah. Yeah, that's. No, I don't find it anymore.
As members.
As member of. Yeah, there we have. Yeah. So here we say, well, if the name is a shadowed name, then you essentially remove this shadowed thing. You use a normal name, but we say we insist on getting the non-private member, not the current private member. And otherwise, our private members are also eligible. You might say, well, what is this thing? Name is shadowed name, and name exclude shadowed names. So we have, since fairly recently, we have semantic names in Dotty now. So names actually have a structure. They have a meaning. So there are certain subclasses. So what we could do here is actually have a look. Shadowed is sort of a particular kind of name that only the compiler needs to know about. It has a legible form, so it's the original name prefixed by shadowed in parents, but that's just for debug printing, basically. It's just essentially some of the names that the compiler is dealing with. So they are all collected in this thing called name kinds, and that's essentially something that avoids accidental errors due to name mangling clashing between different things. Okay, so I think I should stop here. For the types, we covered quite a bit of ground.
Yeah.
But there's also quite a bit of things still left. So I think with other things we need to cover are denotations, came up several times, and also how do contexts go into all of this.
Great. Thank you very much. This was really, really nice, really helpful. Thank you.
Okay. Good. Thanks for staying so long.
Thanks for joining us and for asking questions.
More questions?
Bye.
Bye-bye.